All right, this is called a boom chain problem. We'll have something like a wall, like this is a wall, a side of a building, and there's some kind of a piece of metal or a board or something we call the boom or the bar or the bracket. These are different things we call it. And then there's a chain that comes down here and holds the bar at a certain angle, and then the chain goes on down and supports a weight. So this boom is put in here to kind of make the weight be further out from the wall. So if I remove this boom, this whole weight would come crashing down towards the wall. So usually what we're trying to determine here is what is the force in the boom. Basically, like what is the force that the wall is applying to the end of the boom right here, and then also maybe what is the force up here in this chain. These problems are really, really easy if you assume that the boom has negligible mass. So if we're going to say that this boom right here does not have any mass whatsoever, then that makes this problem really easy. And so in this first problem here, we're going to assume the boom has negligible mass. This first problem, we're assuming that the mass is nothing. Because if it was something, we'd have to actually put a vector right in here that represent the weight of this boom. So if we don't, then it makes it a lot easier. Okay. So we still are usually doing parallel force problems. We don't actually have to do parallel force problems on this one, but we'll kind of do it two ways, and you'll kind of see what we're going to do here. So what we're going to do is we're going to try to figure out what is the force. What is the force in this boom? What is the force that the wall is putting onto this end of this boom? And what is the force in this chain right here? So what we're going to do is we're going to start by making like a measuring or a frame of reference here. And we're going to measure everything from this point right here. And we're going to measure it along the boom. So we're going to kind of maybe pretend that boom is kind of horizontal. And we see that we have a force. We have a force working up this way. And we have a force working down this way. And so if this is my horizontal boom, you'll clearly see that those are not up and downs. They're at angles. And I guess it's kind of important to show here that if this is 60 degrees right here, then this angle here, alternate interior angles, this is going to be 60 also. Okay, so what we're going to do first of all is we're going to resolve these two forces into parallels and perpendiculars, or horizontals and verticals. Now it's not going to look horizontal and vertical because our boom is at an angle here, but I can take this force and say that this force is really the same as a force going perpendicular to the boom, like so, and parallel the boom, like so. And this weight here is a one going perpendicular and parallel also. And I probably should put little arrow heads on there like this. Okay. And we're measuring from this point right here. So if I want to figure out all of these two sides here, the only one I really know is that I know that this weight down here is 1960. And I know this angle in here would be, if this is 60, and this is going to be 30 degrees in there. And so I can figure out what this side is and what this side is right here, first of all. This side here is the adjacent side, so it's going to be hypotenuse, which is 1960. That's the weight, 1960 cosine of 30, 1960 cosine of 30. And so if we figure that out, it'll be 1697.4. 1697.4. That would be 1960 times the cosine of 30. And then this down here would be 1960 times the sine of 30, or basically half of 1960, which would be 980. Okay. Now, what that means is that we know that our ups and downs need to be equal if we're going to try to have this thing all be in equilibrium, which of course is what it is. It's not accelerating anywhere. So the only down I have now is this 1697 right here, down right there, which means that this up here is the only other up. So this one right here also must be 1697.4. So this has to be the same, 1697.4. And if that's the case, then, and I know that this is 80, so this right here must be 10. That means I can figure out what this hypotenuse is and what this other side is right here. So I want to figure out the hypotenuse. It's going to be the cosine of 10. The cosine of 10 will equal adjacent, which is 1697.4, over the hypotenuse. We'll call it h. So the hypotenuse is going to be 1697.4 divided by the cosine of 10, and that gives me a hypotenuse right here of 1723.5. And that's one of the things we had to figure out. We had to figure out what is the force in the chain. And so we just figured that out. 1723.5 would be this force that this chain is pulling up. And if we come up here and figure out this, now that we have a hypotenuse, this side up here would be hypotenuse sine of 10, because it's the opposite, hypotenuse sine of 10. And if we figure that out, it ends up being like 299.3. So what that means is that we have two forces going to the left. This one's going to the left, and this one's going to the left, or down the boom, I guess I should say. And so if we take 980 plus 299.3, we're going to get a total down force of this way. So that means what would be the force that this wall is putting on the boom? Well, it would have to be equal and opposite to those two down forces. So if I add those two up, I know that this wall here is applying a force up along the boom of those things summed together, which is 1279.3. So now I have my force along the boom, and I have the force along the chain, because I measured from this point originally. So I knew that I had my ups had to equal my downs, and my lefts had to equal my rights. I only had two left, so I knew that there has to be a right force, and it must be right here where the wall is pushing up actually along the boom. Okay. Now, so if we write those numbers down here, I'm going to write them down. I want to redo this. So let's just write down the chain. Let's do it up here. The chain force, just so we know that we're going to get the same answer. I'm going to redo this a different way. The chain was 1723.5. That's right there, the force in the chain. And the boom, the force in the boom, or the force like pushing up along here, basically the wall pushing on the end of the boom right here, is 1279.3. I hope that you understand that that's a force that the wall is pushing on the boom. So if I remove that force, basically I remove the boom, the rigid boom, and this whole thing is going to come crashing down to the wall, because there's this force and this force. There's a resultant going this way. And so we're drawing in the equilibrium right here. Okay, so those are my two forces in my chain and my boom. So I want us to look at another way of doing this, because I did this with kind of a parallel force problem. I had this be the frame of reference, and I figured out because this force and this force have to be equal, and therefore the torques are going to be equal, because I have the length of the boom times this plus the length of the boom times this. Those torques would be equal around this point. Okay, so I'm going to whoops, let's see here. All right. There we go. Okay. So now what I want to do, I want to do this problem just a little bit differently. If the boom is negligible mass, which it does in this problem, we can do this problem like just a regular vector addition problem. It's actually very very easy, because all we have to do is we can say that, okay, there's a chain pulling up here with a certain force. There's a weight pulling down here with a certain force. And because this boom has negligible mass, there's no forces coming off of the middle of this boom, we can say that this boom is pushing up here, thrusting up this way with a certain force right along the boom. Now, if this boom had mass, that's not going to be the case. The wall is going to be pushing on this boom kind of, not right along it, but it's going to actually be pushing it kind of up here at an angle a little bit. So I have three forces here, and they all have to be in equilibrium if I add them all together. So if you look at this, the way the boom chain thing is drawn, I have one force right here, it's the boom force. Then I have a chain force actually added on to that. See, tail, head, tail, head, tail, head. Well, that means if I can take my third vector and I can put that in there, it should come down to the tail of the first because I have a net force of 0. So I can take this 1960 here and this weight, and I can actually draw it, that vector, right in here, like so. And I can say, okay, there's the 1960. And what I have here is a pretty simple problem. If I want to figure out the chain right here, or the boom force, I have two angles. Well, I can just do law of sines. I could do sine of 80 over 1960. So the sine of this angle over the opposite side would equal the sine of this angle equals sine of 60 over the opposite side, which is the chain. And if I do that math, you will see that you will get this number right here. And then if I want to do the boom, I can do the same thing. I can do sine of 80 over 1960 equals the sine of this angle, which this is 140, this would be 40. I could do the sine of 40. This right here would equal the sine of 40 over the boom. And if you figure that ratio out, you get that number right there. So the easiest way to do this, if you're going to have if the boom has a mass, you're going to have to do the parallel kind of a method. Parallel force kind of a method, which we're going to do in the next video. But if it has negligible mass, we're going to assume that the boom has no mass like we do in the labs that we're going to do on these. Then it's very easy because we can just say, okay, the boom force plus the chain force, and I can take the weight force over here and put it right into there, and I can have a triangle of all three forces. And I can just use the law of sines to figure out what the boom force and the chain force would actually be. So that makes it a really easy problem. If the boom has mass, the problem is not so much fun. So in the next video, we're going to attempt a boom chain problem where the boom does not have a negligible mass.